the photoelectric effect. Let's start off with what the heck is it? When electromagnetic radiation falls on a metal surface or a metallic surface, so we've got electromagnetic radiation here, and I've tried to show them as photons. They are falling on, or they're incident on, a metal surface. Electrons may be ejected from the surface. So the photoelectric effect in one sentence is electromagnetic radiation falls on a metallic surface and electrons may be ejected from the surface. That is your definition of the photoelectric effect. It can earn you 2 marks in an exam, so make sure you know that. When you use high-frequency incident light, so light like ultraviolet, X-ray, gamma, so on, even blue light, it's more frequency, higher frequency than red, gives the following results. The first result we'll look at on the left-hand side is that electrons are only emitted if the incident radiation is above a given threshold frequency, and that's F0. So that's the first thing that comes out of experimenting with the photoelectric effect. The second thing that comes out of it is that each instant photon interacts with one individual electron. So if you pop in one high-frequency photon, then one electron will be ejected. If you pop in 4 high-frequency photons, 4 electrons will be ejected. Another thing that was found when we experimented with this idea of the photoelectric effect is that when you use low-frequency light, so perhaps red light, infrared, microwaves, radio waves, and so on, no electrons are emitted if the instant radiation is below a given threshold frequency. The metal simply heats up. So if you're using a low-frequency light, no electrons come out and the metal heats up. So by playing around with the photoelectric effect, we come up with 4 observations. And we'll talk through these again because they're important. 1, for a given metal, no electrons are emitted if the instant radiation has a frequency that's below the certain value, called the threshold frequency. 2, the speed of the emitted electrons depends only on the frequency of radiation, not on the intensity. So the speed of the electrons increases as the frequency increases. 3, the intensity only affects the rate of electrons emitted, i.e., the higher the intensity, the more electrons emitted. And 4, the electron was emitted instantaneously. There's no time delay between the photon arriving at the metal and the electron being emitted. It happens instantaneously. And what these observations do is they prove light as a particle. Here's why. Let's look at each individual observation and see why it can't be a wave. Let's see why it has to be a particle. No electrons are emitted if the instant radiation frequency is below F0. So if we were saying, okay, light is a wave, then when you think of light as a wave, energy is spread evenly over the wavefront. Each wave would add more energy to the electron. And eventually, the electron would emit at any frequency. And that's not the observation that was made with the photoelectric effect. The observation that was made followed the particle theory. It said each photon has energy E equals hf. If the frequency of the photon is greater than the F0, which is the threshold frequency, then the energy of the photon is great enough to eject the electron, and that was observed. So first of all, the fact that no electrons are emitted if the instant radiation is below the threshold frequency disproves wave theory and is one in favour for particle theory. The next observation was that the speed of the emitted electrons depend only on the frequency. Let's look at that in terms of wave theory. So the energy of a wave is proportional to the intensity of waves. So if light was a wave, the energy of that light would be proportional to the intensity. Therefore, if you just made more intense light, that would pass more energy to the electrons and they would emit faster, which doesn't happen. So the explanation for this is that light is a particle. And it can be explained by E equals hf. Therefore, greater frequency meant greater energy of photon and greater emitted speeds of electron. And that was observed. The third observation, let's look at both wave theory and particle again. Electron emission was instantaneous. If the wave was instant for long enough, and this is if you're looking at light as a wave, then enough energy would eventually transfer and an electron would be emitted, but with a time delay. So if you put visible light onto there, it's got a low frequency, and you left it on for long enough, eventually it would pass enough energy to the electron, it would be emitted. And that is not the case. What happens is above a certain frequency, one photon interacts with one electron and it is emitted immediately. So we have three observations of the photoelectric effect, three main observations, and none of them can be described and justified through wave theory. They can only be described or justified by particle theory. And that meant that this was a great historical significance. The photoelectric effect was a massive historical significance for physics. The photoelectric effect proved that there's a photon theory of light. And that's what he received his Nobel Prize for in 1921. He proved that light is a particle and it comes in the form of a photon. He proved that light is not necessarily a wave. There are a few things I'd like you to take away about using the photoelectric effect. And the first thing that you should know, and it's dead easy, are the keywords, because these are the two definitions that are most prominent with the photoelectric effect. The threshold frequency, you need to memorize this one, is the minimum frequency of electromagnetic radiation required to release an electron from the surface. And work function is the minimum amount of energy required to release an electron from the surface of a metal. We know the energy of a photon is E equals hf, so the work function, which is the minimum energy required to release the electron, must be E equals hf naught. And f naught is the threshold frequency. Let's look at the photoelectric effect in terms of the conservation of energy. Let's look at this system here. The energy going into this system comes solely from the energy of the photons. So the energy of the photon is E equals hf. So the energy in is E equals hf. When the photon reaches the metal surface, it provides a certain amount of energy to release the electron from the surface. And we call that the work function. So this value here is a value of the work function, and we can write it as E equals hf naught. Any energy that's left over is given as kinetic energy to the electrons and they fly away. So we've got energy in is the energy of the photon, being instant, equals the energy out, which is the energy given to release the electron, plus the subsequent kinetic energy of the electron. And this formula here you'll be asked to use quite a lot in problem solving. Okay, so let's dive into your revision note template. Write down what the photoelectric effect is. We talked about that in the first slide. The definitions you'll want to memorise are that of the threshold frequency and work function. You'll also want to put in your equations section the equation for the photoelectric effect. That's the one we talked about with the conservation of energy. And finally, in the other notes section, I really think you should put some time into explaining why the classical theory of light cannot explain the photoelectric effect. And we'll dive into that a little bit deeper when we look at the past paper questions in step 2. I've jumped to my sketchy notepad and I want to take this idea of hf equals the work function plus kinetic energy. I want to take that a little bit further. Let's rearrange that slightly. Let's call that EK first of all to make it a bit simpler. So let's say EK is equal to the work function, that's on the other side, so minus work function, plus hf. So EK is equal to hf minus the work function. Just rearranged this formula here. If we were to plot a graph, we could have that on the y-axis. We could have this on the x-axis. we could have that as a gradient and this as an intercept. So we're basically trying to recreate y equals mx plus c, which is our straight line graph. So let's try that. Let's plot this graph. So we'll have that on the y-axis, and we'll have EK there. We'll plot an x-axis, but instead of the x, we'll put our frequency of radiation. That's in joules and hertz. And we're going to have a positive gradient. So the line is going to be a straight line with a positive gradient. And you can see here that that's a negative intercept. So we have our negative intercept there. So the line's going to look like that. So if we take a particular metal and you plotted the kinetic energy of the electron against the frequency of the incident radiation, you'd find a line that looked like that. And the gradient would be h, which is a constant. That's Planck's constant. This might be for a metal, say, zinc. Okay? So from this graph, you can find a couple of things. You could calculate the gradient, and that would tell you what Planck's constant is. You can calculate or determine what this intercept here is, and that would tell you the threshold frequency. Oops, I'm just getting frequency wrong. And you can use this value here to tell you what the work function of that metal is. Now, if you were to take a different metal, like magnesium, you'd find a line that looked a bit like this. It still has the same gradient because the gradient is equal to Planck's constant, and that has to stay the same, so the slope will be the same, but your threshold frequency might be slightly different, and your work function, you might need more energy to release the electron. So if you see a graph with kinetic energy on the y-axis and frequency on the x-axis, you need to instantly realise three things. One, that the gradient is constant. It's not any constant, it's equal to Planck's constant. Two, that the intercept on the x-axis is equal to threshold frequency. And three, that the y-axis intercept is equal to the work function.
If we go back to the learning objectives, you'll see that we've covered the first graph you need to understand when looking at the photoelectric effect. To understand the second two graphs, you need to know about something called the photoelectric experiment. And the photoelectric experiment is very heavily examined. In fact, the majority of marks when dealing with the photoelectric effect is around this experiment. I'm going to take some time to explain the experiment in full detail and then approach these two graphs based off that experiment. Here's a diagram of the photoelectric experiment as you would see it in an exam. And we split this experiment into three parts. Part 1 up here, Part 2 down here, and Part 3 down here. We're going to talk about each part in turn. Part 1 of the photoelectric experiment is where photons are released from a beam of light or from a lamp. These photons are released down here. These photons have energy E equals hf. And of course we'll remember that these photons are released from the atom. And it's to do with electrons jumping down different energy levels and a photon is released. That's part 1 of the photoelectric experiment, is considering the photons that are released from a UV lamp or an X-ray or something, a relatively high frequency lamp. Why are we talking about high frequency? Because part 2 is the photoelectric effect. Let's look at part 2 in detail. We have something here called a photoelectric surface. It is a metal surface and it has work function phi. That means the photon that's incident on it from part 1 needs to have enough energy to overcome the work function in that metal surface. So the energies instant on here have to have energy greater than HF0, where F0 is the threshold frequency. That's why I tend to talk about UV lamps or high energy lamps at this stage. So in the photoelectric surface, the photon has enough energy to overcome the work function, and it releases electrons with kinetic energy. With looking at part 2 of the experiment, we're going to use equations like HF equals the work function plus kinetic energy. Of course, you can write that HF equals the work function plus half mv squared, because that's just another way of writing kinetic energy. We could write HF equals HF naught, because that's a different way of writing the work function plus half mv squared. There's different ways of writing that one equation, but the fundamental equation comes from there, and that's the crux of part 2. And part 3 of the experiment adds an extra element. What happens in the photoelectric effect in part 3 is they put a high voltage across that photoelectric surface and they add an extra cathode and anode. This is negative, this is positive, part of the cell. So that means this is a negative plate and this is a positive plate. We call the positive side the cathode and we call the negative side the anode. And the value of voltage across this cathode and anode can be anything. That's what this arrow here means. It means that it can be anything. And it can go from 0 all the way up to any value of voltage. Let's consider when the voltage across it is 0. So when V equals 0, the electron energy is equal to EK, or a half mv squared. If we were to increase that voltage, and let's say we make it 1 volt, what we'd find is we start to have an electric field across these plates. And the electrons would start to gain electric potential energy. And that electric potential energy is opposing the current direction of the kinetic energy, because the electrons are moving towards a negative plate, so they're repelled. So when V equals 1, the electrons experience electric potential energy, which opposes the kinetic energy. And the value of that electric potential energy is W equals QV. We're not dealing with Q as in the charge on any particle here. We're dealing with the charge on an electron. So our work done on that electron that opposes the kinetic energy is EV. And when there's 1 volt, then the work done that opposes that kinetic energy is 1 electron volt. When there's 2 volts, it's 2 electron volts, and so on. What that means, if you have an electron that's travelling in this direction with kinetic energy, and it's experiencing opposing electric potential energy in the opposite direction of 1 electron volt, then the kinetic energy of that electron is the kinetic energy of the electron minus 1 electron volt. Or if it's 2 volts across it, then it's the kinetic energy of the electron minus 2 electron volts. And eventually what will happen is if you increase this voltage enough, then the kinetic energy of the electron will equal the opposing electric potential energy, and the electron will stop. And that voltage is called the stopping voltage. You will find many exam questions on this experiment alone, which means you will have to recognise the 3 parts of the experiment. There are, of course, examples in step 2, activate the application. We hit it head on and we do really difficult questions first. So if you're worried about this, don't worry, head to step 2 and we'll talk about this in great detail. Let's move on to the graphs. For a first very simple graph, we're just going to consider part 2 and we're going to do a close-up on that. I've drawn that here. we have our photons with energy E equals hf. They're instant on our photoelectric surface. And as a result, as long as the photons have energy to overcome the work function, these electrons leave with kinetic energy. I want to introduce the definition of current here. The definition of electric current, I, is the rate of flow of electric charge. So in this situation here, to increase the rate of flow of electric charge, we can do one of two things. We can increase the number of electrons that pass a point per second, or we can increase the speed of the electrons that pass the point per second. If we relate this back to the photoelectric effect, to increase the flow of electric charge, by increasing the number of electrons, that means we simply increase the number of photons. Or increasing the speed of the electrons means we increase the energy of the photons. Either way, what we're doing is we're increasing the intensity. Because the intensity is defined as the energy per unit area per unit time. A lot of students think that increasing the intensity in the photoelectric effect means increasing the number of photons, but actually you can keep the same number of photons but increase the energy of those photons to increase the intensity too. So why am I telling you all this? Well, the relationship that comes out of this is if you increase the intensity, you increase the current. So increasing the intensity up here at part 1 increases the current here at part 2. And we can plot a graph for that. It's not one of the graphs listed, but it has been examined before, so I'm going to put it in just now. It's a really simple one. Intensity on the x-axis and current on the y-axis, and a nice straight line showing one of direct proportionality. Let's isolate that graph just to make it a little bit clearer, and this graph shows the variation of photoelectric current with intensity of instant radiation. That is one graph you might come across, but it's not the graphs mentioned in the learning objectives. So let's continue. I now want to add the voltage across that photoelectric plate and look at the electrons as they're emitted and what happens when we increase the voltage. And the graph we're going to look at now is one that looks like this. The x-axis is voltage and the y-axis is current. If you imagine there's 0 voltage across that photoelectric plate, then the current is the maximum it's going to be. The electrons have got their kinetic energy, their beam of light is instant on it, and the intensity is the maximum it's going to be. So the current is going to be like this. And we call that our reference beam. However, as you increase the voltage across this photoelectric plate, eventually what's going to happen is that the electric potential energy, EPE, which is of course QV, equals EV, is eventually going to equal the kinetic energy of the electrons. And at that point, when they're equal, the kinetic energy is going to come to 0 and the electric potential energy is going to be maximum. When the kinetic energy comes to 0, the rate of flow of electrons, which is the current, is also going to be 0. So at a certain point, the current is going to be 0. And we call that point on the x-axis the stopping voltage. Between the electrons having maximum current and the stopping voltage, we're going to see that current decrease, and it takes a little pattern that looks like that. Let's think about what happens when we alter the beam incident on that photoelectric plate slightly. Let's imagine we have the photoelectric effect here. We have photons of the same frequency, but less of them. That's going to decrease our intensity, because intensity is the energy per unit area per unit time. So if we have less photons, there's less energy per unit area per unit time. And when we decrease our intensity, we decrease our current, as we saw earlier. So for this situation where we have this photons with the same frequency, but less of them, we're going to find that the maximum current is less. However, the photons have the same energy, which means they have the same stopping voltage. So we're going to still have our end point here, but our graph is going to look slightly different. It's going to look like that. Let's consider another situation. Let's consider the photoelectric plate here. We have photons incident on that photoelectric plate. This time, the photons have a lower frequency, which means the energy of the photon's less, but the intensity stays the same. And if we have the same intensity, it means we have to increase the number of photons to keep that intensity the same. How does that affect this graph? If it's a lower frequency of radiation, that means HF equals the work function plus kinetic energy. That's smaller, that stays the same. So that means the kinetic energy of the emitted electrons is smaller, which means that the stopping voltage is smaller. So if we have a lower frequency but the same intensity, what we'll find, the current comes to zero at a smaller stopping voltage but has the same intensity, i.e. the same current, as the reference beam. I understand this is difficult, but when you come to step 2, activate the application, you'll start to see how these are applied in exams. The final graph I want to look at still looks at the photoelectric experiment. And we're looking now at section 3, and this is section 3 is this part here where the electrons have their kinetic energy and are moving across this cathode and anode, and we got this stopping voltage applied which is opposing it. At this stage, we're looking at the photoelectric effect equation, HF equals the work function plus kinetic energy. What I'm interested in is creating a graph that shows how the stopping voltage, V, varies with wavelength. I'm interested in those two concepts. And to do that, we need to rearrange this formula here to have stopping voltage on the y-axis and wavelength on the x-axis. Let's tackle wavelength first. Instead of HF, we can have HC over lambda. Why can we do that? Well, C equals F lambda when we're looking at light. F equals C over lambda. So instead of putting E equals HF, we can put E equals HC over lambda. So we're happy with that. That brings our equation to this. Want to know about stopping voltage? Well, when the electron stops, work is done on the electrons to bring it to a full stop, and that work done is the charge on the electron times the voltage, and of course, because we're dealing with electrons, that gives us EV. So our equation becomes HC over lambda equals stopping voltage plus EV. I want to have V on the y-axis, so I'm going to rearrange this equation. I'm going to say EV equals HC over lambda minus the work function. And I want to have V on its own on this left-hand side, so I'm going to divide everything by E. V equals HC over E lambda minus the work function over E. This is a constant, this is a constant, this is a constant, this is a constant. What that means is we can separate that out like this. V equals HC over E, 1 over lambda minus work function over E. This will go on our y-axis. This will go on our x-axis. This will become the gradient, and this will be our y-intercept. It looks like this. We know that it's a straight line, It's a positive gradient because this is positive, and it's got a negative intercept. So the line, our gradient looks like this, and it is equal to hc over E. This is a constant, this is a constant, and this is a constant. So that gradient shouldn't ever change. If we had a metal with a different work function, you'd see a line that looks like this. It has the same gradient because the gradient is a constant, hc over E. That gradient has to be the same, but what you'd notice is that the y-intercept is different because the work function of that metal is different. That is the work function 1 for the first metal, and that's work function 2 for the second metal. But the gradient would be the same. You'd also notice that when voltage is 0, there's 2 points where it crosses the axis, and those 2 points are different wavelengths, which represent the different threshold frequencies. Instead of having 1 over lambda on this x-axis, you could have C equals F lambda. So 1 over C equals 1 over F lambda. 1 over lambda equals 1 over lambda equals F over C. So you could have F over C on this x-axis. You might find also that the graph is shown without the C's because it's a constant that comes up. You might find that the C is out, but that's all right. You can deal with that. And in which case, this becomes your threshold frequency. The learning objectives have listed 3 different graphs you need to be comfortable with for the photoelectric effect. I've actually shown you 4. I strongly recommend you get these 4 graphs down in your common graph section of your revision note template. I also strongly recommend you go to the common experiment section or the other notes section and give full details of the photoelectric effect experiment. This will be key in gaining as many marks as possible in your IB physics exams. If you don't believe me, head to step 2, activate the application, and you'll see just how prominent these graphs and this experiment is.
And here we are back on the slides. So if your instant energy, let's look at this side of the table here. If the energy of the instant photon, HF, is less than the wave function, then nothing happens. The energy of the photon is not enough to overcome the work function, and the metal may heat up, because that energy's got to go somewhere, but it's not going into releasing the electron. If the energy of the instant photon, HF, is equal to the work function, then the electron will just be released from the metal surface, but will not fly away, as there are no excess kinetic energies available for that electron. And finally, if your energy of the instant photon is greater than the work function, the electron will be released from the metal surface and will fly away with maximal kinetic energy of kinetic energy equals HF, which is the instant energy of the photon minus the work function. Some important notes: the work function is equal to phi equals HF naught. 1 photon interacts with 1 electron. The electrons are emitted immediately after the interaction with the photon. There is no time delay. And the ejection of the electron is sometimes called photoemission or photoelectric emission.
We've taken a really deep dive into what the photoelectric effect is, how it explains the photon theory of light, and how you're going to be examined on it. We finished up by putting a really simple summary and some important points about the photoelectric effect. It's time now for you to note that summary and those important points, and then complete questions 1 to 12 in the knowledge questions. In the previous section, we explored the idea that light, which we previously thought of as a wave, can actually also be thought of as a particle. And now we're starting to look at a concept called wave-particle duality. Can it be both a wave and a particle? And it would only make sense, and it would only be fair, if we took something we thought of as a particle, let's say an electron, and see if we can do the same. Can we think of it with particle qualities? And can we think of it with light qualities? Let's investigate. Before we delve into whether an electron is a particle or a wave, it's important to get clear what we associate particles being. And I would say that particles have the following properties. They're hard. You can see these particles inside a box here. They're hard and they have mass. They're very small. Well, I think electrons very small. And when they bump into each other or collide, they obey Newton's laws. So from my point of view, very clear, an electron is a particle. Well, if I was to think of an electron as a wave, I'd want the electron to have wave-like properties. And wave-like properties are they transfer energy, they can reflect, refract, diffract, and undergo superposition. And you'll remember all of those actions that waves take from the waves topic. So now we understand the properties of a particle and the properties of a wave. What properties do we expect electrons to show? And it's this experiment setup that Davison and Germer used to prove that electrons can behave both as particles and as waves. In this experiment, we start with an electron gun. And this electron gun is going to fire out electrons. Those electrons are fired out as particles, little small, hard balls. And they're accelerated from a negative plate towards a positive plate. That acceleration is provided by a high accelerating voltage below. And of course, E, V, which is the work done on the electron, equals half mv squared, because all of that electric potential energy is transferred over to the kinetic energy of the electron. So we can work out the speed of the electron as it hits that positive plate. And all of these equations relate to particles. However, everything changes though when the electrons hit the thin graphite screen. And when I say thin, I mean thin. It's literally a couple of atoms thick. Very thin graphite screen. And what they noticed, good old Davison and Germer, was that a diffraction pattern was evident on the end of the screen. And that confused them. Well, you may think, well, it's not that hard because you pop lots of electrons through, then some electrons hit here, one hits there, some electrons hit here, one hits there, some electrons hit here. And we have ourselves regions of high intensity electrons hitting the phosphorus screen and regions of low intensity electrons hitting the phosphorus screen. That's why you've got an intensity pattern. But it's not true. Because when you put just one electron through that thin graphite screen, you still noticed these diffraction rings. So one electron was causing that diffraction pattern, which meant that one electron was behaving as a wave. And that was absolutely mind-blowing for Davison and Germer, because what it proved was that electrons have wave-like properties. They can be treated as particles at certain times, and they can be treated as waves at other times. They have wave-particle duality. Let's simplify that experiment slightly, because this is the kind of thing you'll see in your exam. So go to the simplified experiment, and you'll see we have the electron beam hitting this very thin sample of carbon-12, which is another word for graphite. Carbon is graphite, and graphite is carbon. And the electrons are then diffracted through this graphite. And that diffraction pattern causes an intensity pattern on the screen. And you'll recognise that intensity pattern. You saw it when we were studying diffraction in previous topics. When you take your detector and move it all the way down, continuously down, increasing the angle from this central line, the intensity pattern you see is shown on this graph here. And what's clear is there is an intensity pattern that matches a diffraction pattern. It's a similar pattern to that of a single slit diffraction. I just want to remind you at this stage, a single slit diffraction can be one of two things. It can be where the wave goes through a single slit and diffracts, like this. It could also be where the waves diffract around an obstacle and you actually end up with a diffraction pattern like this. Now, this is extra to the syllabus, but so when you're diffracting around a thin graphite screen, what you're actually diffracting around is a series of very small nucleus. And each of those very small nucleus is causing this diffraction pattern, which gives this intensity pattern. And that intensity pattern is similar to that of single-slit diffraction. Because it's similar to single-slit diffraction, we can use the equation sine theta equals lambda over d. Now, technically, if you're a science whiz, it should be sine theta equals 1.22 lambda over d because it's a circular aperture. But for the purposes of IB physics, we're just going to go with sine theta equals lambda over d. I've got a bit of a warning here. This equation is not in the data booklet. And I beg you, every time you see this intensity pattern to do with electron diffraction, I beg you to write that equation down because it won't be given to you anywhere. It's not in a data booklet and you do have to use it. Now, I know what you're saying. You're saying, Sally, fine, use it, but what does it all mean? Well, theta is the first angle of minimum diffraction. That's this angle here. Lambda is the wavelength of the electron. And d, try and fit this in somewhere, go around here, whoop, is the diameter of the nucleus. So in theory, if we can find out the wavelength of an electron and we can analyse the intensity pattern, we can work out how big a nucleus is by a simple experiment. That previous equation requested that we use the wavelength of an electron, and we haven't actually discussed that yet. So de Broglie did that for us. He said, after analysing Davison and Germer's experiment, he said it's not just electrons actually. I think all particles can display wave-like properties. And he came up with the equation for the wavelength of any particle with mass. His equation is lambda equals h over p. P, of course, is momentum, and lambda is wavelength. And this is the classic wave-particle duality equation because it finds a relationship between the wave-like properties of an object with the particle-like properties of an object. This is our wave-particle duality equation. And of course, we've extended it a little bit to say lambda equals h over p, which is equal to h over mv, because p equals mv, momentum equals mass times velocity. Let's have an example of that in action and calculate the wavelength of an electron travelling at 1.2 times 10 to the 6 metres per second. We use the de Broglie equation. We say lambda equals h over p, which equals h over mv. M is obviously the mass of the electron, v is the speed. We've got both of those things, and we've got h, which is Planck's constant. We pop all the numbers into the equation, and we get our wavelength of the electron to be this. The wavelength of the electron changes because the faster it goes, if we increase the speed, then the smaller that wavelength becomes. Let's note that down. I'd like to remind you of the basics of diffraction. That's the size of the gap. And these are the waves with a wavelength. And if the wavelength is equal to the size of the gap, we get maximum diffraction. So if we want an electron to diffract around a nucleus, we need to have the electron's wavelength of a roughly the same size as a nucleus. And let me tell you that this wavelength of 6.1 times 10 to the minus 10 metres is far too big. We need that wavelength to be smaller. How do we make the wavelength smaller? Well, we speed the electron up. There's a limiting factor on how fast we can make that electron go. We can't make the electron go any faster than 3 times 10 to the 8 metres per second because that is obviously the speed of light. So for this electron diffraction to work, we need to have the electron travelling at very fast speeds, but not within the relativistic speeds of the speed of light. Let's revisit our question at the start of this part of the tutorial. Is an electron a wave or a particle? Can it be reflected? No. Can it be refracted? No. Can it be diffracted? Yes. Is it a particle? Does an electron have mass? Yes. Is it compact? Yes. Does an electron obey Newton's laws? Not that we know of. So, our electron can exhibit both wave and particle-like behaviour, just like light. So with that in mind, let's head to your revision note template. Write down what qualifies as particle and wave behaviour. Of course, wave behaviour is, can it be diffracted, can it be reflected, and so on. Particles are, does it have mass, is it compact, and so on. Then, write down how electron diffraction proves that the electron exhibits wave-like behaviour. Draw the intensity pattern graph and the equation, which is, of course, sine theta naught equals lambda over d. Remember, that's not in the data booklet. And note down the de Broglie equation. Note down that you can find the wavelength of any particle using this equation here. An interesting aside is that you can work out your own wavelength. Let's do it. 6.63 times 10 to the minus 34 divided by my mass, let's say, is 65. And let's say I run at 100 metres in 10 seconds, so 10 metres per second. By the way, it's very generous to say that I would run 100 metres in 10 seconds. I'd have to be Usain Bolt to do that. My wavelength, if I was running in a 100 metre race, would be 1.02 times 10 to the minus 36 metres. Am I ever going to find a particle small enough to diffract around? No, I think I'm safe. So I am not going to be diffracting anytime soon. But those poor electrons are accelerated close to the speed of light, just might. And finally, can you complete questions 12 to 17 in the knowledge questions? We've reached the final part of this tutorial and it's back to light again. We previously proved that light had particle qualities using the photoelectric effect. And we know, of course, from even GCSE physics that it's got wave-like properties. In the last section, we looked at the electron and we said, yep, it's got particle properties because they can collide, they can have mass or compact and so on. And it's got wave-like properties because it can diffract. And we were really investigating this idea of wave-particle duality. Compton and Compton scattering is further evidence that light exhibits particle qualities. So another piece of evidence for light being a particle is Compton scattering. Let's look at Compton scattering in more detail. I think you'll agree, in that last video we were looking at two particles colliding. And when those particles collided, there was a transfer of energy and momentum. That caused this ball, initially at rest, to gain energy and change direction. The particle that was moving towards it lost energy and also changed direction, and that's because of this transfer of energy and momentum. What Compton realised was that if you collide a photon with an electron, the same thing happened. The photon lost energy and changed direction. And how do we know that? Well, after it's collided, the wavelength is greater. And also it's pretty obvious it's changed direction, right? So we know it's lost energy because its wavelength has increased, which means that the frequency has decreased. And it's changed direction. If you look at the electron, after the collision, it's gained energy and it's changed direction. And the fact that a photon could transfer energy and momentum to the electron, just like any particles of mass, convinced Compton that the photon had particle-like properties. He also took it one step further and came up with a good equation. And like any good physicist should, you'll remember that after the collision, the photon lost energy because it transferred some of that energy to the electron. If it loses energy, that gets smaller, that means the frequency of the photon gets smaller, which means the wavelength of the photon after the collision should be greater. So the final wavelength is greater than the initial wavelength, which means that final wavelength minus initial wavelength should be a positive value, delta lambda. And once we have that change in wavelength of the photon after and before the scattering, we realise that it's directly related to the angle of scattering. And the angle of scattering, and this is very important, is for the photon. Because you'll notice that the electron also scatters by an angle, and we'll call that phi. But the angle we're interested in with this equation is the photon scattering angle. It's worth noting that Compton scattering has never been in the IB syllabus before. It's new to 2005, so you won't find as many past paper questions on it initially. This equation really genuinely is quite easy to deal with. It's time for you to head to your revision note template and note down the following. The diagram of the Compton scattering, just like the one that I've been working from in previous slides. Note down that Compton scattering demonstrates the particle nature of light, which of course, so does the photoelectric effect. Write down the effect of the collision on the photon energy and the wavelength. Of course, the photon loses energy. Finally, write down the Compton scattering equation, which you will find in your data booklet. And to test out this very simple equation that looks scary and hard, please head to question 18 in the knowledge questions.